Today I'll be talking about Casper and the consensus protocol that we're going to be using for the RChain blockchain. So I'm just going to go a bit over what we might have gone over last time, but the idea is the RChain state is just a giant Rolang term. And so consensus is all about how do we replicate this giant RChain or Rolang term, and how do we ensure that people can submit stuff into this state and have it replicated across machines. And so the idea is that, well, there are special contracts that govern how the blockchain goes. And that's sort of what's listed here. Most essentially, there's the proof of stake contract. And so the idea with proof of stake is that, unlike with proof of work, people put in bonds, which are tokens of some value that can be used to stake for the protocol. And the idea is that once you bond, you're committed to helping the protocol move forward, or else you get penalized in some way. And so the idea is that, well, first, the essential building block is, of course, the block. And blocks contain parents to other blocks. This is the same as many other blockchains that you'll be familiar with. And they also contain the hash of the current state and then justifications, which I'll go more into later. Actually, let's go on to the next slide. One more. Yep. So this is sort of a visual representation of what the RChain block would look like. So starting from the body of it, we have the new code. This is all the deploys or the Rolang terms that are going to go into the block. And so if we covered anything last time about Rolang, basically any new terms that you want to include into the state will go here. And so the idea is once you've included those terms and then you've run through them, you get a post state. And that's sort of, or that is what is listed there. So the post state is stored inside this data structure called a state trie. This is the same with Ethereum. And so finally, you have the reduction receipts. And so the idea is that Rolang has some non-determinism to it. But in order for nodes to be able to replicate this, we need to add reduction logs. And so those will be included there. And then so all this information gets hashed up and stored in the header. So we see the equivalent new code hash, the post state hash, the reduction receipts trie hash. And so the only really new element in that header is the parents. And so what the parents is of course, what this block's parent is. In RChain, we allow for multiple parents, so then it's a parents list. And then when you combine that all, the question was why there are multiple parents. And the answer is so that you can include blocks that contain non-conflicting transactions. Essentially, this is an issue about throughput. If you can include blocks that have multiple or non-conflicting transactions, then you can include both at the same time instead of having to recreate another block with the same transactions as the ones that you were about to include. So, I mean, it's not like it's not too critical to the platform that we have multiple parents. It's one way that we're trying to get more throughput, and we'll essentially experiment with it as we go on. Effectively, what I've sort of listed here is almost the same as what Ethereum has. And the only difference is actually, I would say, the justifications, which I haven't really explained so far. But this is because we're using a proof of stake model. And so in a sense, we're not really improving what Ethereum is doing in terms of how we're laying out our block. You can say that we've adjusted our new code section so that it takes in Rolang terms instead of EVM opcodes. Or
you're building upon kind of an already developed one, and then you're just kind of adding it to it to make it work with the product.
Exactly. Yes. And so, oh yeah, I see. The question was how is RChain's block different from sort of traditional blockchains? How is it better? And yeah, I was just explaining that. And so, but I do want to go over the aspect of proof of stake and why we need justifications. And so, in traditional blockchains or proof of work models, all you need is a block hash that is lower than some number, sort of signifying that you've gone through and done a lot of hashes. But in RChain's model, we have proof of stake, which doesn't require that. In essence, it makes creating blocks almost free in comparison. And so, but what's important is that, well, you justify what you're building on top of. And so, one thing we don't want is for people to just create arbitrary forks. And the way we ensure this is there's only one possible way, or there's a deterministic way to determine the parent based on the justification. And so the justifications, it's a generic term. For RChain's purposes, we can call it the latest block. And so what actually is inside these justifications are pointers to what other validators have created as their last block. I just want to make sure that everyone understands this diagram first. So what you see here is a blockchain, or it's technically a block DAG. But you have two validators. They have their own column. The Genesis block is something that has no validator or creator, so to speak. But yeah, I've arranged it this way to sort of have it easily shown. But the idea is that these circles represent blocks. And the arrows that you see here, the solid ones, are parent pointers. So if we start from the top left, and we can go down, and then we go down right, and then down left. That is the main chain starting from the block in the top left. And similarly, from the top right, we go down, and then down left. So that's the main chain from the top right block. And so the idea is that each validator has a different view as to what is the main chain. And in fact, there's technically three perspectives here. There's the perspective from the left validator, and then there's a perspective from the right validator, and then the perspective that we are viewing sort of from the outside world, or we can consider ourselves as a validator with no weight in this protocol, and that would be a third perspective. And so just to go on, the dashed lines, the dotted lines, are justification pointers. And so this is what is saying what the other, or what each block, when created, that validator saw as the latest block from another validator. And so just to be clear about that, so you should always see a dotted arrow from one block to every other column, right? So in theory, you should see two justification pointers here for each block, but you don't. And that's because it's implied that the parent is one justification pointer. And if you don't see an arrow or a dotted line from one validator to another, it's implied that it's the same as the previous. So one example of this is if you look at the second from the top right, there's no dotted arrows to anywhere. And that just means that that validator on the left thinks that the latest block from the validator on the right is just a genesis block. And if, to be clear, that everyone starts out believing that everyone else has seen the genesis block, and that is their latest block. And so the idea is that based on what other validators have shown is their latest block, you build the chain. So is there anything that's not clear about this diagram right now? Yeah. So yeah, thank you. Yeah, I'm assuming that time goes up, and I've sort of staggered. I've staggered the diagram such that on every row there's only one block, but it's possible that two blocks get created at the same time. And just for the sake of simplicity, I've listed it out this way. So the question was, how do you handle two blocks being created at the same time? I guess what you're implying is like, which one do you build on top of, right? And so in Bitcoin, it's really easy in the sense that, well, you just build upon the chain with the highest difficulty, right? And you'll never get two blocks to the exact same hash, or that's actually a good question now you think about it. But but in proof of stake, it's a bit more complicated because creating a block is free. So you want to ensure that you're always building upon the right one according to the protocol. And so the way to do this is we go through a process called ghost traversal. And so in order, to be clear, each validator has a certain weight. And this weight is determined when they've sort of bonded in. And so we're assuming that the validator on the left has a weight of 2, and then the validator on the right has a weight of 3. So what we do is every time we want to check or figure out which block are we going to build on top of, we go through the chain and we start scoring the blocks. And so what we do is we take each validator's weight and we see which block they support, essentially their latest block. And then we go down the chain and we start adding up the values. And so here we see how we start at the top left for the left validators column. And we go down and say, OK, the validator with weight 2 supports the top left block. And then it also supports its parent, and then that's parent. So it adds 2 to the entire main chain. And so then we do the same process for the right validator. We add 3 this time to each in the main chain. And so when the two validators support this, they both support the block, you get the number 5 because, well, 2 plus 3 is 5. And then so that is the score from the perspective, the score of the various blocks from the perspective of the outside viewer. And so now what you do is you want to find out, OK, which one's the tip. And so what you do is you start from the genesis block, and then you go up so you have 2 options at the start, right, between 0 and 5, and you take the one that is larger. And so you go up to 5, and then you get another choice between 0 and 5, and then you go up 5 again. And then now you have a choice between 2 and 3, so you go up 3. And so what you're supposed to build on is the top right block, right? So that's how you resolve ties, because you'll always, even if 2 validators create the same block, they'll be scored differently according to this. Can we go to the next slide? Yeah, and so the path that you take up to the tip of the block, or the tip of the chain, that is called the fork choice. And I mean, you can think of it as, when each time there's a fork, you choose one side. So it's your fork choice. And then so the idea here is that, yeah, that path is what you want to display on your block explorer. Navneet. Cool. Okay. So now we want to get on to like finalizing blocks. So it's cool that we can decide, okay, given a block DAG, what we're going to build on top of. But now we want to know, okay, so now we have this chain going on, but which blocks are safe? Or which can we say that the transactions in here are going to stay in this chain as the protocol progresses? And so what you do is you go along the fork choice, and you start with the genesis, and then you go up to the next, what we call candidate, and then we see whether it's safe. So then we run the safety oracle. That's the algorithm that determines whether this block is safe or not. And if the safety oracle says yes, Navneet, then we mark it as finalized, and then we go on to the next block. And so, okay, so what is, okay, I've sort of glossed over what is the safety oracle. So I'm going to explain that now. So the specific oracle that we're using for RChain is called the Klieg Oracle. And so to understand the Klieg Oracle, we have to go back to what a clique is. And so a clique is, so the idea is, this is a graph, right? So clique comes from graph theory. And the idea is that there are a number of vertices here and edges between them. And so what a clique is a connected or complete subgraph. Or technically it's called the induced complete subgraph. And so each vertex here is a one vertex clique. And so each edge that you see forms a two vertex clique. And so what we're interested here is in the maximal clique. And so there are two maximal cliques here. They're both in dark blue with 4 vertices. And the reason why these are the maximal cliques is because there's no clique with 5 vertices. If you can see, there's no graph with 5 vertices or subgraph with 5 vertices that is complete. And so in this example, 4 vertices is the maximal clique. And the idea here is that, well, you can arrange your validators in terms of this graph. And then you want to find out sort of the biggest clique. And if the maximal clique of the graph is greater than half, then you know that there's no way for you to sway the decisions within the clique. And so that's sort of the principle of this oracle. And I'm going to explain the details of how you actually run it. So I'm just going to go back, and we're going to go back to the place that I glossed over in terms of here's the candidate that we want to see which we want to run the Klieg Oracle over. And so the way we do this is, we build the agreement graph. This is the graph that I was mentioning earlier to determine what the maximal clique is. And so we start out with each validator being a vertex in this graph. And the idea is that, and then we erase all the lines at first. And the right circle is a bit, or vertex is a bit bigger because that validator represents the one with weight 3, which is greater than the one with weight 2. So that's just why it's drawn that way. But if we go on to the next slide, we want to see whether we're allowed to draw an edge between them. Whether, in this example, we want to see whether there is a 2 vertex clique. There's only 2 validators, so that's by definition the maximum clique if it exists. And so the first condition, there's 4 properties that we need to fulfill if we want to draw an edge between them. And the first one is whether the first validator sees the second validator agreeing with the candidate. And so again, as a reminder, the candidate is that number 1 block down there. And we do see that indeed the validator with weight 2 sees, because if you see that justification pointer, right, that is what it sees as the other validator's latest block. And that validator's latest block does contain in it the candidate. And so that's sort of check number 1. And then we want to go the opposite direction. Next slide. So yeah, we want to go the opposite direction where the validator with weight 3 sees that the validator with weight 2 agrees with the estimate. And so those are the 2 properties. But there's 2 other properties that are more subtle. If we go on to the next slide. Yeah, so you might think like nothing changed here, but it was actually just that coincidentally it matched up to what we wanted. But the idea is that we want to make sure that the first validator, the validator with weight 2, never sees, will never see that the validator with weight 3 is going to disagree. And so I've highlighted these 3 circles because, well, we want to start from the number 2 block that's not highlighted, because that was the one that we saw was the latest block, or what the validator weight 2 saw was the latest block from the validator with weight 3. We want to look at all the blocks above that. In this case, there's only one, which is the top right block, number 3. And we want to see that does agree with the estimate, and it indeed does. And so we repeat the process the opposite way. And so in this case, we have to look above the unhighlighted number 2 block, which is, so the 2 that we need to look at are the number 3 block and the number 4 block. But the number 4 block, or the number 3 block is the parent of the number 4 block. So if the number 4 block does indeed satisfy this, we're good. And then so we can see that the number 4 block, from there, if we follow it down, it has the candidate in the blockchain of the number 2 block on the right side. And so basically, all 4 checks have been passed now. So if we go on, yep. And then so now we can draw an edge between them. And so here, we can stop because, well, there's no more edges to check for. And we know that there's a maximal clique of 100% of the total weight. So everyone will always say that the number 1 block, that candidate would be included as the protocol goes on. So yeah, and then so what we do then is we go on to the next block, and we just repeat the process. So we do this again where the validator with weight 2 sees that the validator with weight 3 agrees with the candidate, and it does because the candidate is the latest block that it saw. And then if we go backwards, we see that, oh, this time it doesn't work out because the candidate is that number 2 block, but the latest block that the validator with weight 3 sees points to a block that is below it. And so it doesn't, we can't see the fact that the validator with weight 3 sees that the validator with weight 2 is agreeing with the candidate. And so because of this, we're not allowed to draw that line. And so in this case, the maximal clique is the one with, it's just a 1 vertex clique. And then so it's just the one with the largest weight, the validator with weight 3. And so as a result, we can't finalize that number 2 candidate. And so this is kind of what we do. And so the idea is that you only have to run this oracle when you're curious if a block should be finalized or not. So you can, another way to put it is you never actually have to run this oracle. If you don't want to be, if you just want to kind of look at the chain and say like, oh yeah, it's buried, like 2 billion blocks down, so there's probably no way that it's going to get reverted. you probably don't want to do that for anything critical, but the idea is that this is just a way to confirm that your block is safe, and the protocol can otherwise build without it. Actually, sorry. So yeah, this is just an example with multiple parents. Yep, Chris. I see. So the question was, how do you know? Well, first of all, is it how many validators should be in the in the protocol, and what are their weights? So we actually haven't decided specifically what we want to set as, whether we want to cap the number of validators, or whether we want to allow validators of arbitrary stake. As you probably figured out, the more stake you have in this protocol, the more control that you sort of have over the building of its blocks. And so it's sort of an open question. And so the Klieg Oracle, I'm not sure about the asymptotic analysis of the performance of the Klieg Oracle in terms of the number of validators. It definitely is at least O of n, because as you add more validators, or strictly, it's because assuming that all the validators have the same weight, then you always have to make sure that there's essentially, if you double the number of validators, you sort of have to double the amount of checks that go on. In fact, because of the way the graph is aligned, I would like to say it's O(n) squared, but it's not necessarily the case that you have to go through each edge, if that makes sense. You don't have to go pairwise, because at some certain point you can be like, oh, there's enough edges, or on the converse, you can be like, oh, well, these are large enough nodes that if there's no edge between them, then there's no way that there's going to be a maximal clique of some size. Yep. So I guess the question is, how do network upgrades work? And so the tricky thing is, well, you have to make sure that, in traditional blockchain protocols, what usually happens is you specify a height, right? And you say, at block 3,000 or something, we're going to do this hard fork or whatever that changes some certain properties about the block or how consensus works. And I think it's in the same, it's going to be, for the single shard case, I think we're going to do it the same way. We're going to choose a block height such that after this block, we're going to change the properties.
See it like version 2 of the software.
Yeah, exactly.
Otherwise, you can't participate in the.
Yeah, and so then it becomes a sort of voting, right? So at that, so you sort of state that up front, and then you include that as sort of you can, if you can, you want to specify it as a contract, or you want to change an internal Roland contract to, for example, you want to change the proof of stake contract. But if you can't do that, you'll have to do it through, I guess, some Scala source code. But in either case, you'll have to figure out, what you want to do, and you have to propose that to the community. And if people decide not to follow that procedure, then the protocol just goes on, if that makes sense. Mm-hmm.
Right? So
the question was essentially, because of the throughput that we want to get and how nodes could be distributed around the world, is there a possibility that we'll get a network partition, and when we get that network partition, we'll end up with people trying to double spend on either side of the partition? And so if you're running the safety oracle as we showed, you should basically, in that case, you should never get finalized blocks, right? Because you'll have 50% of the weight on one side of the world, and then 50% of the weight on the other side of the world. And you need more than 50% of the weight to finalize a block, right? So essentially, if it's a true equal split, right, you'll just never have any finalized blocks until someone from the other side of the world makes that bridge and then comes in and then allows that safety oracle to say, yep, this block is safe. Yeah. So it will be a case where essentially, you won't, the network will be slowed down as a result, of that network partition. Yeah. The question was, does each validator have a copy of the whole blockchain? And so for within a single shard, every validator keeps the entire block DAG technically for that shard.